So last class I was talking about the second law on the definition or the statement that defines a property, which is called entropy. And it's a really difficult thing to grasp at first or at second. What is the entropy? But we saw this. This is the second law. This is the mathematical formula that was given to us by Rudolf Clausius and talk about an inequality. Okay, so inequalities, which is just by it, it's a little bit weird. Okay, all of the conservation laws in nature are creating with equal. Now these things are non-equal, so there's something really fishy here. Okay, so yeah, indeed it is. In the physical part, at least, it is something different. Okay, there is not a conservation law. So this thing that some of the books call balance of entropy is actually not a balance. Okay, but nonetheless, we're gonna use a little simple trick that we're gonna say, so, okay, so this delta of entropy, we don't know too much about it, but this delta of this property, it's higher most of the times than the heat divided by the temperature, okay? So therefore, what we have here is that if we do this scenario, okay? So yeah, forget about it. So we can actually write this as an equal, so Q divided by T, and let's just put another thing here so it can counter the delta S, okay? So now, delta S is the change in entropy, which is it's a property that we don't know too much. It appears in the steam tables, but we don't know too much so far. Now Q is the heat transfer, and T it's temperature. And S gen is entropy generation. Entropy generation. Oops. Okay, or something like that. Okay. Well, at least that's the name. Look something here. It appears a heat, but it doesn't appear the work. Okay, so the work doesn't appear here. It's a little bit of strange, right? So maybe you recall the first law for closed systems, which was this. So now you have the delta in some property, which is called internal energy, should be equal to the heat transfer plus the work transfer, or another way to transfer energy, which is called work. Okay, so why doesn't work appears here? It is something strange is happening here. Okay, so it seems that if you want to increase the entropy here, okay, so let's just put some transfer of heat. Okay, but no work. So it seems that work has nothing to do with the increase of entropy. Now, this is a fundamental difference between heat and work. This is a way of, I'm going to call energy transfer without, I'm sorry, just the opposite. Oops. Just the opposite of it. With that, always. Oh, I'm having such a good time here. So energy transfer that always carries entropy. How so? Well, look, buddy, this is the entropy that this heat is carrying. So this is an entropy. Yeah, this is entropy transfer. Now, what about work? Well, I don't know too much, but work is energy transfer that never carries or introduces or put out, or whatever you want to call it, never carries entropy. Never. So it seems that work it's far more efficient than heat in order to transfer energy. This is something which is fundamental. Okay, imagine that instead of having heat sources, we had work sources. And you will say, well, yeah, I haven't thought about it. Okay, most of the things that we do, this is a fundamental thing for the guys that are gonna go and build power plants or whatever you wanna do something regarding energy. But for example, if you are gonna do something with heat, we have heat sources, okay? I should say energy sources. Most of our energy sources, you hit something, you burn something. So most of the time it's just combustion. Okay, so combustion most of the time. So yeah, I know that we are trying to forget about these combustion processes in order to produce energy, okay, or electricity. And the idea is to go to something which is called, green energy or something like that, whatever you want to call it. But the idea is that you still, or most of the time, what you do is you hit something, okay, in order to produce combustion and then to produce something useful, which is electricity. Electricity. But what you don't find in nature is this already. Okay, you don't find electricity already. So maybe to add for your confusion, electricity, you can say that electricity equals work. They are kind of the same thing. Okay. How did you get this stuff? Well, okay. So I'm just trying to give you the general sense of this. You don't have to be an expert. You don't have to go too deep into it. I'm just showing you some differences. So the first thing is that Q and W are not equal. They are never equal. So it seems that for us humans, if we want to do some useful effect, so we need to burn something or to hit something. We cannot just go and dig something and find in mines a work source. We cannot, I don't know, we cannot say, okay, so let's just raise our eyes into the sky and see a work source. We don't find that. We need to build it. How so? Imperfectly. We go from this place, which is imperfect. Why it's imperfect? Okay, because you will carry this guy over here. So these imperfections will lead you to the electricity, but we cannot find this guy already there. Okay, so um, this is again the example that I gave you, the last one. The last one was that, you had air plus gas, okay, fine. And at the other stage you had smoke, or okay, so gases, okay. Let's just be more formal. So gases. Delta U was equals to 0 because this guy was an isolated system. Therefore, no Q, no W. Therefore, the energy should be the same one. But you can put this into your car, and this thing will give you 100 kilometers independence. Okay, so this you can drive around your car for about that. And in this case, you just get to, I don't know, 10 meters if something was really, really right, because most of the time it will never even get on, right? So you cannot turn on your car if you put the gases into that. But why not? It has the same energy. Well, it seems that at this point, this is one and this two. At this point, so S1 has some low entropy, and in this case, you have the same energy but with high entropy. This is something fundamental again. So energy, you can start thinking about it. So energy has two shades of it. What do you mean? Yeah, you already know the quantity because you have used the first law and see something about, okay, so how many kilojoules do you need in order to move around the piston and blah, 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 okay? So quantity, you have this stuff, but also energy has quality. I know it's gonna sound a little bit weird, but 10 kilojoules are in the first law, it's equals to 10 kilojoules, right? And you will say, yeah, right. This is so obvious, right? This is just dumb. Well, buddy, these 10 kilojoules may produce a lot of work. For example, 10 kilojoules of work. And these 10 kilojoules can use, and let me just say, you can use these 10 kilojoules in order to produce 10 kilojoules of work. And maybe there are another 10 kilojoules that won't produce a thing of work. Why? How so? Well, something was lost from this point to this point. Something was lost. What was lost? Well, okay, so that's why the entropy is like a measurement of the dispersion of energy. Something was lost from one place to the other. And most of the times that happens. Okay, so let me just go back to this, our beeline in this story, which is the S-gen. Okay, so S-gen. Again, this S-gen. If this guy increases, then all things go to hell. Okay, so that's what that's something that you may need to learn. So let's just put it. S-gen. S-gen can be positive. Okay, it can be equals to 0, and it cannot. Let me just from the start, can be negative. Okay, so if this thing is positive, then we call this process as irreversible. Maybe you have seen that stuff, or maybe a real process. That's what it's, a real process, something that was actually made in our universe. Okay, now this is a reversible process. This is a reversible process, or maybe I can call it an ideal process. In the best of circumstances, we can almost achieve this S-gen equals to 0, which then will give us that this guy is equals to 0. Therefore, delta S equals to Q divided by T. Okay, so in the best of the cases, we can expect that. But most of the of our, I will tell you about this later. But most of the of our phenomena cannot let us do that. And this thing is actually, and virtually, not virtually, but actually impossible. So you cannot produce something like that. What if you can? Well, okay, if you can do this. So if you think that this thing is right, that this guy can be negative, therefore, then your gases can take you to 100-kilometer car ride. Okay, that's what it will mean. It will also mean that, just for to give you another example, that, for example, you have coffee here. It is a, I don't know, 70 degrees Celsius. I think I exaggerated with that number. Let's just put 50 or whatever. Okay, so 70. And you are, this is a room, okay? So this thing is in a table, and you're gonna dissipate heat into a room, which is at 20 degrees Celsius, for example. This thing happens, okay? So you can apply the first law and second law and to see that that's actually will happen. It will happen until you have this situation. You have this situation where the coffee is now at 20 degrees Celsius, and or I don't know, maybe if you're gonna be if you're gonna put yourself into hair splitting, you can say, well, okay, so let's just put 22 degrees Celsius, and the room is also at 22 degrees Celsius. Okay, so maybe something increased there. It doesn't really matter. The idea is that they got into an equilibrium, but you have not seen this. You have not seen that maybe spontaneously. That's a really big word in thermodynamics. This thing is at 20 degrees Celsius. uh, this guy is, I don't know, let's just help the example. This thing is 30 degrees well, just put well, no, I don't want to help the example right now. So why not, this is 20 degrees Celsius to the room, you know, the room, and nothing is happening here, okay, because these guys are in equilibrium. But why not, if this thing happened, why not the other way around? Maybe you can do that. This guy increases, I don't know, to 70 degrees Celsius, but now the room is not at 20 degrees Celsius. Maybe now the room is a, I don't know, let me just put a minus 10 degrees Celsius. Okay, so now the room is that. And the first law will tell you, okay, fine with me, you can do that. At first, they are in equilibrium, 2020, and now the time has passed, and you can actually find that this guy is 70 degrees Celsius, your cup of coffee is hot again, but now the room is it should be okay, because it needs to be a little bit colder, okay, but that doesn't happen. That actually doesn't really, never happens. Okay, so something is wrong here. This thing, it happens, okay, and this thing never happens. Why not? What is going over there? Well, okay, so what I'm going to tell you, if this entropy generation should be negative, then you can actually heat spontaneously cup of coffees by lowering the temperature of the room. And you will say, oh, that sounds like an entrepreneurship idea, right? Well, the thing is that the universe, at least this universe, won't let you that happen. Okay, so let's just mention how can you produce entropy generation. So you have a physical sense of what this abstract thing over here is, right? So, okay, so maybe you produce combustion. Okay, you are in the right way to be an irreversible process. Okay, so combustion is so imperfect in the sense that you are using a really structured material, which was the gas over here. Okay, this thing is compact and structured, and then it just disperses away into a gas. Okay, well, that thing actually produces irreversibilities, or it's gonna make your process irreversible or real. Okay, so this thing can happen. It happens all the time. Well, what else? Well, mass transfer. If you produce mass transfer, it will happen the same thing. Well, I don't know about mass transfer. What the hell is that? Well, for example, maybe you have seen if you just put this a fishing pond or whatever you want to put it. This is a tank full of water, and you put, maybe you place a drop of ink here, right? So if you, this is what will happen if you go for 2 hours and look at the tank of water again, maybe you will see this. This will happen. This always happens. It never happens the other way around. Another idea of this impossibility. It never happens that you have a lot of ink dispersed in the water, and then you go and in the next 2 hours, everything whoop just goes into a point like the one that you did first with this point or dot of ink that you put in the water. Well, that never happens. Well, therefore, mass transfer is also a entropy generator phenomenon. Okay, so what else? Heat transfer. Well, our billing here, which is heat transfer. Whoops, is there something else? Yeah, turbulence. Turbulence produces the increase of entropy generation. Well, you know, why? Well, because of viscous dissipation, actually. Just be a little bit more formal, viscous dissipation. So all this known, maybe one more that maybe you didn't think about. Well, friction, buddy. Well, friction. So all this stuff will produce a little bit of heat that can never do something useful as work. That's the whole idea. Something about this phenomena here, they will produce a little bit of the energy that will never do something useful. That's the whole idea of entropy generation. Okay, so for our purposes as engineers, this is very important because maybe we're using, you know, we are using a really high temperature steam into a turbine and try to figure it out how what which one, which path will be the best in order to squeeze the juice, the energetic use of that steam in order to produce the more power, the more possible power. Well, okay, so what we need to think about is, well, let's just try to lower this guy over here. Okay. Well, that's it for today. So, whoops. See you guys.